Heat transfer can also occur via the electromagnetic spectrum via thermal radiation. This is the only heat transfer mechanism that does not require molecules or atoms or particles or some sort of mass to transfer energy. The electromagnetic waves transmit the energy. But unlike waves we're familiar with, such as ocean waves, electromagnetic radiation does not require a medium. This is an important point. So although without water you can't have an ocean wave, you can transmit light through the vacuum of space. And clearly, if this was not the case, it would be impossible for the sun to transmit heat energy to the Earth. Some important points, as we shall see, is actually that all things emit and absorb energy at the same time according to their temperature. In fact, this is strongly dependent on the temperature. It's temperature to the power of 4. Some things emit radiation that we can see, such as a hot toaster element, but most heat is emitted in regions of the electromagnetic spectrum that our eye does not detect. We can use an infrared camera to start to see the world of heat radiation. Here's an infrared image taken of a group of people. I'm down the front with a cold nose. The rate of emission of heat energy via radiation is given by the Stefan-Boltzmann's law. This is that the rate of heat transfer, Q over T, or the power, joules per second, equals epsilon sigma A T to the power of 4, where the epsilon stands for the emissivity of the material. This is a dimensionless constant. Sigma, which is the Stefan-Boltzmann constant, it has the value of 5.67 by 10 to the negative 8 joules per second per meter squared per Kelvin to the negative 4. Area in meters squared, and temperature to the 4th power. Now, it's important that the temperature is in Kelvin here. Note the strong dependence on temperature. This is not a linear relationship by any sense. It's to the power of 4. So this is telling us that the heat flow is proportional to temperature to the power of 4. Let's talk a little bit more about the emissivity. Dark materials are both good absorbers and radiators. They have high values of epsilon. High values equal close to 1. While shiny materials, such as a metal, reflect most of the radiation and have low values of epsilon. So epsilon equals 1 equals a perfect radiator and perfect absorber, where E equals 0, so it's not absorbing or radiating any heat, is a perfect reflector. The value of epsilon for humans is approximately 0.97, and remember there's no units. This value is independent of skin color. The Stefan-Boltzmann law is concerned with the net flow of radiant emission. And it's important to understand that this is always a two-way street. A body will both emit and absorb energy at the same time. And this is the basis of many questions that are asked on this topic. You should always remember that just because a body is cold doesn't mean that it's not emitting radiation, and just because a body is hot, it is not absorbing radiation. So to work out the net power, we can say that the P emission equals this, and the P absorption equals this. So our net P equals P emission minus P absorption, or epsilon sigma A T1 to the power of 4 minus T2 to the power of 4, where T1 equals the temperature of the object and T2 equals the temperature of the environment. So if T1 equals less than T2, then P net will be negative, i.e. the heat will flow from the environment to the object. Think about what will happen if T1 equals T2. Of course, then P net will equal 0 joules per second. There will be no net heat flow.